For this one, I want to state where the function is increasing and decreasing, relative maximums and minimums, and then state the end behavior. So increasing and decreasing, I always read this thing from left to right. Here the function is going down, and then the function starts going back up, and then it goes down again, and then up again. All right, I'm just following the path of the function from left to right. When it's going down, it's decreasing. And really, I just tell this like a story of my x values. From here, from forever until I got to this value, it was decreasing. So I label that this way. From negative infinity to a negative 3, it was decreasing. I'm listing the x values. From here to here, it was also decreasing. Okay, from 0 to 3. So I say from 0 to 3, it was decreasing. And then increasing from here to here, it was increasing. So from negative 3 to 0, it was increasing. And then from here on up, from 3 to infinity, it was increasing. Okay, and this is interval notation. Remember, the parentheses mean that those values are not included. And they're not included because these values are local maximums and minimums. They're turning points. Infinity can never be included. And so when we look at the relative maximum, there's only one of those, and that's this guy right here. That's at 0, 0. That's an ordered pair versus interval notation. Relative minimums, there are two of those. There's this one right here, which is at negative 3, negative 4. But then there's also a relative minimum right here at 3, negative 5. Okay, so it's okay to have more than one relative maximum and minimum. It just means it's higher than the points around it, which each of those minimums are, for minimum, lower than the points around it, which each of those is. Okay. End behavior, I'm always looking as x goes to negative infinity, and then as x goes to positive infinity. And really, essentially, this is saying, look at the far left of your graph, look at the far right of your graph. And when I look at the far left of my graph, that's this end right here, I just look at what the arrow's doing. It's going up, which means my f of x, my y values, are going to positive infinity. And then looking at as x goes to positive infinity, it's telling me to look at the far right of my graph, which is this arrow right here, which is going up. So f of x is going to positive infinity. And that's end behavior. Okay? Number 31, it asks us to state the end behavior. And for this one, we're still going to do the same thing. We're going to look as x goes to negative infinity, and then as x goes to positive infinity. But really, we have to plug these in. When it's written in standard form like this, we essentially ignore everything except the thing with the highest exponent. So we're looking at this term right here. And I'm just going to plug it in. Right? If I were to plug this in and do a negative infinity to the 6th power times a negative 2, well, negative infinity to the 6th power is a positive infinity, and then times a negative 2 is a negative infinity. So that gives me the end behavior. It's telling me that when I plug a negative infinity in, I get a negative infinity out. And that's it. All right? I do the same thing then with positive infinity. Let me hit the reset button here. If I plug a positive infinity in, positive infinity to the 6th power is a positive infinity, times a negative 2 is a negative infinity. So that also gives me a negative infinity. And that's it. Okay, that's end behavior. We're just plugging each of those in one at a time. For the next one, I'm essentially going to do the same thing. The only difference here is I have to plug it in for each of these because I don't have this thing in descending order. Okay? So this one, I'm going to plug a negative infinity in. So I've got a negative x squared. It doesn't matter the plus 3 or the times 2 minus 1. Really, we're just going to plug in a negative infinity to each of these. And see what I get. Here I get a positive infinity, and then times this negative. Here this one's already a negative infinity, and this one's a positive infinity. So what it really has is negative times positive, which is a positive. So when I plugged a negative infinity in, I got a positive infinity out. So that's my end behavior. And I'll do the same thing with positive infinity. So I've got a negative x squared. I've got this guy, and then I've got another squared term, and I'm plugging positive infinity in this time. So that gives me an infinity with a negative sign tacked on the outside. Here, this one's an infinity as well. So I have negative times a positive, which means when I plug the positive infinity in, looks like I get a negative out. And that's it. That's end behavior. Applying end behavior to a graph is what we're going to do in number 33. For this one, we want to sketch a possible graph of this thing. And we're just going to do a real quick sketch. So for this one, I'm going to identify my x-intercepts. Here I find out that x equals 0 when I set this equal to 0. Here I set the x plus 5 equal to 0. And here I set the x minus 2 equal to 0. And I solve each. This one's already solved, x equals 0. This one, of course, I subtract the 5. This one I add the 2. So I get these x-intercepts. All right, that's the first thing I'm doing. I'm identifying the x-intercepts. So now I have x-intercepts. I've got 0. I've got a negative 5 back here somewhere. And I've got a positive 2 up here somewhere. Okay, so I've got my x-intercepts. The other thing I'm going to look at is I'm going to look at how many times each of these x-intercepts occurred. This is what we call multiplicity. Okay. So the multiplicity, since there was an x squared, it means I would get that x equals 0 twice. So the multiplicity here is 2. There's only one of these, and there's 2 of these. Because that was an x minus 2 squared, I would get that solution twice. And really, the multiplicity tells me whether this thing is going to touch the x-axis or pass through the x-axis to give me that x-intercept. When the multiplicity is even, it touches. When it's odd, it passes through. So this one is just going to touch. This one is going to pass through. And this one's going to touch. And so now I'm going to use my end behavior and some of that information to draw the graph here. When I find end behavior as x goes to infinity, so if I plug an infinity in, I want to see what f of x is going to do. Let's start with negative infinity. So that's going to give me a positive times a negative times a positive, which is a negative. And then when I plug a positive infinity in, it's going to give me a positive infinity out. And really what that's telling me, it's saying at the left end of the graph, this thing's going to be going down forever, which means my function should be going down this way. At the right side of my graph, my function should be going up forever, so it's going to be going up this way. And I would just start drawing a quick sketch of this thing. I know it's going down over here. As I approach the x value of negative 5, my multiplicity tells me to pass through. As I approach 0, it tells me to just touch at that point. As I approach 2, it tells me to just touch at that point. Now I know it's going to continue up forever. And that's it. So multiplicity, along with the end behavior, gives me a real brief, quick sketch of this thing. And really that's important because now I can clearly identify approximately where my relative maximums and minimums are going to be. Okay? For the next one, we just wanted to state whether or not this one is a solution. And you could actually plug the 2 in and see if you get a 0, but an easier way to do it is actually use synthetic division. Remember, synthetic division can be used to test solutions, so I plug the 2 into my box. I write down my coefficients in descending order. I bring this guy down, I multiply, I add straight down. I multiply, I add straight down. I multiply, I add straight down. And really what I'm looking for is to see if this thing divides evenly. Remember, my factor remainder theorem says that whatever I get right here is the remainder. That's what I would have gotten had I plugged that x value into the equation. So this one is not a 0 because I did not get a 0 out for my remainder. And then it wants me to do the same thing with a positive 4. So I plug a 4 into the box. So I write down my coefficients. Bring down that first one, I multiply, I add straight down. I multiply, I add straight down. I multiply, I add straight down. And so this time I get a 0 there, which means this one is a 0 of the function. When I plugged it in, I got a 0 out. Okay? And then if we want to find the remaining zeros, essentially what we've done here is I took this guy, x equals 4, and proved that it's a 0, which means if I think about the factor that that came from, if I work backwards, it means that x minus 4 is one of my factors. Okay? Which means that what I've really done here, if x minus 4 is one of my factors, and when I used the 4 in synthetic division, if I divided that out, it left me with this guy right here, which interprets into an x squared plus 8x plus 15. So what I've done is I've essentially factored this thing through division, and now I can finish solving by factoring if this whole thing is equal to 0. I build a bridge here. 2 numbers that multiply to a 15 but add to an 8 are a 3 and a 5. And now I can set each factor equal to 0. I already had this factor equal to 0, but it's fun to do it again. Again, this is the one I already had when I add the 4 to each side. I end up with the x equals 4. But these are the two remaining that I'm looking for here. I subtract the 3 from each side, so I find out that x equals a negative 3. Here I subtract the 5, and I find out that x equals a negative 5. So those are my three solutions. Negative 5 and the negative 3 were the two remaining solutions, the two that I did not have before. And that's it. So I'm essentially factoring by division. For this one, it asks us to solve the polynomial completely, find all the zeros. So really, it's just like the last problem, except I'm not giving you that first 0. We have to guess and check. And really, we're going to start off with factors of negative 8. So it's something like 1, 2, 4, 8, and then the negative versions of each of those. And I'm just going to take a guess. All right? I take a guess at one of these things. Maybe I'll guess something like a 2, and I'll plug it in and see what happens. And so when I plug the 2 in, I bring this guy down, I multiply, I add straight down, I multiply, I add straight down. It's not looking good. That one is not a 0. So I try again. That one didn't work. I can cross that one off of my list. All right? So I try something else. I try something like maybe a negative 2. And I write down my coefficients. You're not necessarily going to get this on the first try. You have to do a little guess and check. And now I multiply, I add straight down. I multiply, I add straight down. I multiply, I add straight down. And it turns out that this one is a 0. Okay? So in other words, x equals negative 2 is one of my solutions, which means this thing factors into an x plus 2. That's where I get the negative 2 from. And then the x squared minus 3x minus 4. And then I can finish solving this one by factoring. I've already got the x plus 2, and I already know what that's going to give me. This factors into an x minus 4 and an x plus 1. And now I set each factor equal to 0, so I get a negative 2. Here I add the 4 to each side and get a 4. Here I subtract the 1 and get a negative 1. That's it. Okay, so you have to arrive at the first one by guess and check, and then you factor from there. This one's the same thing, so I do a little bit of guess and check. Now I'm looking at factors of negative 10. So 1, 2, 5, and 10, and then the negative versions of each of those. And I just take a guess. Maybe I'll guess something like a negative 1. So I bring down the 1. I multiply. I add straight down. I multiply. I add straight down. I multiply. I add straight down. And that one didn't work. So I try again. So maybe I'll try something like a positive 2. I bring this guy down, I multiply, I add straight down, I multiply, I add straight down, I multiply, I add straight down. And that one happens to work, which means I've got an x minus 2 as one of my factors. My other factor is the x squared minus 4x plus 5. And now I can try building a bridge, two numbers that multiply to a 5 that add to a negative 4, but it's not going to happen. I can't solve this quadratic right here. This one I can solve. And I get x equals 2. This one, x squared minus 4x plus 5, I can't solve by factoring, so I either have to do completing the square of the quadratic formula. I'm going to do completing the square. I'm going to subtract the 5 from each side, x squared minus 4x with a little space equals a negative 5. I do b divided by 2 and square it gives me a 4. Whatever I do on one side, I have to do the other side. That's an x minus 2 squared equals a negative 1. I take the square root of each side. So I find out that x minus 2 equals plus or minus I, and then I add the 2 to each side. So the reason I couldn't finish solving this one with factoring is because it's two complex solutions. So what I get here is I get x equals 2 as one of the solutions, and I get the 2 plus or minus I as my other two solutions. And that's it.